Every single day, architects around the world design buildings with glass walls that reach toward the clouds, creating stunning skylines that define modern cities. The Empire State Building uses over 6,000 windows, while the Burj Khalifa contains enough glass to cover 17 football fields. But here's what's absolutely incredible. Each massive glass panel in these skyscrapers starts as ordinary sand and must be manufactured to tolerances more precise than spacecraft components. A single bubble or stress point could cause a panel to explode 50 stories above the street, making architectural glass one of the most demanding manufacturing challenges on Earth. Today, we're breaking down the extraordinary process inside one of the world's most advanced architectural glass facilities, where panels weighing over 800 pounds and measuring larger than garage doors get created with precision that ensures they can withstand hurricane force winds while providing crystal clear views for decades. Make sure to subscribe as we explore the incredible engineering behind creating the glass that shapes our modern world. The journey begins with the same ultra-pure silica sand used for the finest optical glass, but architectural applications require massive quantities that would supply smaller glass manufacturers for months. Mining operations extract silica sand from deposits that formed over millions of years, with purity requirements so strict that iron content must be kept below 50 parts per million to prevent the green tint that would make building glass unacceptable for architectural use. Transportation of raw materials to architectural glass facilities involves specialized rail cars and trucks designed to handle hundreds of tons of sand while preventing contamination that could affect final glass quality. Storage silos at the manufacturing facility can hold over 5,000 tons of silica sand in climate-controlled environments that maintain optimal moisture levels for consistent batch mixing throughout the year. Batch preparation for architectural glass involves precise mixing of silica sand with soda, ash, limestone, and specialized additives that create glass with properties specifically engineered for building applications. Unlike container glass that prioritizes strength, architectural glass must balance optical clarity, thermal performance, and weight considerations that affect building structural requirements. Computer-controlled mixing systems ensure that each 12-ton batch contains exactly the right proportions for consistent glass properties. The massive furnaces used for architectural glass dwarf those found in other glass manufacturing facilities, with melting chambers capable of containing over 800 tons of molten glass at temperatures exceeding 2,900 degrees Fahrenheit. These industrial giants consume enough natural gas every hour to heat 4,000 homes while maintaining temperature uniformity across their entire volume to ensure consistent glass quality. Advanced combustion systems use computer-controlled gas injection and air mixing to create optimal flame characteristics that heat glass uniformly without creating hotspots that could cause quality variations. Oxygen enrichment systems increase flame temperatures while reducing emissions, enabling the high heat transfer rates needed for melting massive quantities of sand into pristine glass suitable for architectural applications. The float glass process represents one of humanity's greatest achievements in materials manufacturing, creating perfectly flat glass surfaces with optical quality that rivals polished mirrors. Molten glass flows from the furnace onto a bath of liquid tin at precisely controlled temperatures, spreading across the metal surface under its own weight to form sheets with uniform thickness and flatness that would be impossible to achieve through any other manufacturing method. Temperature control during the float process requires incredible precision because the glass must remain hot enough to flow and level while cool enough to maintain dimensional stability. The tin bath operates at temperatures between 2,000 and 1,800 degrees Fahrenheit, with heating zones that gradually cool the glass as it moves across the 70-foot-long bath. Advanced temperature monitoring systems track glass temperature at dozens of locations, making automatic adjustments to maintain optimal conditions. The float process creates glass ribbons up to 12 feet wide and virtually unlimited in length, flowing continuously across the tin bath at speeds carefully controlled to achieve desired thickness. Glass thickness gets determined by the speed at which the ribbon moves across the tin bath, with slower speeds creating thicker glass and faster speeds producing thinner sheets. Precision speed control enables thickness accuracy within plus or minus 0.02 of an inch across the entire glass width. Edge trimming systems use diamond cutting wheels to create perfectly straight edges, while the glass ribbon is still warm enough to cut cleanly without chipping or stress formation. These cutting systems must operate with incredible precision, because edge quality affects both appearance and structural performance of finished architectural panels. Automated cutting systems can adjust ribbon width in real time based on production requirements and quality measurements. The annealing process gradually cools architectural glass, following precisely controlled temperature schedules that prevent internal stress formation while maintaining optical clarity. Annealing layers stretch over 400 feet in length, providing controlled cooling environments where glass temperature reduces from over 1,000 degrees to room temperature over several hours. Temperature control during annealing must be accurate within 5 degrees to prevent stress patterns that could cause spontaneous breakage years later. Quality monitoring throughout the float process uses advanced optical systems that detect surface defects, thickness variations, and stress patterns invisible to human inspection. Laser interferometry measures glass flatness to tolerances measured in fractions of wavelengths of light, while automated stress detection systems use polarized light to identify internal stress concentrations that could affect long-term performance. The continuous glass ribbon emerging from annealing represents the raw material for architectural glass panels, but transforming this pristine material into building components requires additional processing steps that enhance performance while maintaining the optical quality achieved through float manufacturing. The transformation from basic float glass to high-performance architectural panels begins with coating processes that apply incredibly thin metallic layers designed to control heat, light, and energy efficiency. These coatings are so thin they measure only 15 billionths of a meter, yet they can reflect infrared radiation while allowing visible light to pass through, creating glass that keeps buildings cool in summer while maximizing natural lighting year-round. Magnetron sputtering systems create these advanced coatings by bombarding metal targets with high-energy particles in vacuum chambers, causing metal atoms to deposit onto glass surfaces in perfectly controlled layers. The process takes place in chambers with vacuum levels so extreme that air molecules can travel several feet without hitting anything else, preventing contamination that would ruin the optical properties of these precision coatings. Silver-based low-emissivity coatings represent the most advanced architectural glass technology, reflecting up to 90% of infrared heat while maintaining over 70% visible light transmission. The silver layers must be protected by barrier coatings that prevent oxidation and corrosion, creating multi-layer systems with up to 17 individual layers, each precisely controlled to achieve optimal performance characteristics. Temperature control during coating application requires precision that rivals semiconductor manufacturing because even small temperature variations can create coating defects that affect both appearance and performance. Glass temperatures must be maintained within plus or minus 3 degrees throughout the coating process, while chamber temperatures stay constant to within 1 degree to ensure uniform coating thickness across panels that can measure over 12 feet wide. Quality control for coated glass involves optical testing that measures light transmission, reflection, and color properties, using instruments calibrated to detect variations invisible to human vision. Spectrophotometers analyze coating performance across the entire light spectrum, while color measurement systems ensure that coated glass matches architectural specifications for buildings where color consistency across hundreds of panels is absolutely critical. Cutting operations transform large glass sheets into individual panels sized for specific building applications using water jet cutting systems that can slice through glass up to 2 inches thick while maintaining edge quality suitable for structural glazing. Diamond cutting wheels score glass surfaces while controlled braking systems apply precise pressure to separate panels along scored lines without creating chips or stress concentrations. Edge polishing removes microscopic flaws created during cutting operations, because even tiny edge defects can propagate into cracks that cause panel failure under building loads. Automated polishing systems use diamond grinding wheels and progressively finer abrasives to create perfectly smooth edges with radius specifications measured in hundredths of an inch. The polishing process also removes stress concentrations that could lead to thermal breakage when panels experience temperature changes. Drilling operations create holes for mounting hardware using specialized diamond core drills that can penetrate thick glass without creating stress fractures around hole edges. The drilling process uses continuous water cooling to prevent thermal shock while maintaining cutting speeds that balance productivity with edge quality requirements. Automated drilling systems can create holes positioned to tolerances within 1/16 of an inch across panels, measuring over 8 feet in length. Tempering transforms ordinary glass into safety glass through controlled heating and cooling processes that create permanent stress patterns, making glass 4 to 5 times stronger than standard float glass. Tempering furnaces heat glass panels to over 1200 degrees Fahrenheit before rapidly cooling them with precisely controlled air blasts that create surface compression stress while leaving interior zones in tension. The tempering process requires incredibly precise timing because glass must reach exact temperatures throughout its thickness before rapid cooling begins. Temperature monitoring systems use infrared sensors to track glass surface temperatures, while embedded thermocouples measure interior temperatures, ensuring uniform heating that prevents distortion or breakage during the tempering cycle. The entire heating and cooling process takes less than 10 minutes, but requires temperature control accurate to within 5 degrees. Tempered glass safety characteristics result from the controlled stress patterns created during rapid cooling, causing panels to break into small cubic fragments rather than dangerous sharp shards if damaged. This safety feature makes tempered glass mandatory for many architectural applications, particularly in areas where human contact is possible or where falling glass could create safety hazards. Heat strengthening provides an alternative to full tempering for applications requiring increased strength without the complete stress transformation of tempered glass. Heat-strengthened glass undergoes similar heating but slower cooling that creates intermediate stress levels, providing twice the strength of standard glass, while maintaining better optical quality for applications where visual distortion must be minimized. Laminated glass construction bonds multiple glass layers together, using transparent plastic interlayers that hold fragments together if breakage occurs, creating safety glass that remains in place even after impact damage. The lamination process uses specialized ovens that heat glass and plastic layers while applying pressure that eliminates air bubbles and creates permanent bonds between all components. Insulated glass unit assembly combines multiple glass panels separated by spacers and sealed around edges to create window systems with superior thermal performance. Automated assembly lines position glass panels with precision measured in thousandths of an inch while applying structural sealants that must maintain weatherproof seals for decades while accommodating thermal expansion and building movement. Gas filling of insulated glass units replaces air between glass panels with argon or krypton gas that provides better insulation properties while reducing heat transfer through convection. Gas filling operations take place in controlled environments that prevent moisture contamination while achieving gas purity levels exceeding 95%. The improved thermal performance can reduce building energy consumption by over 20% compared to standard air-filled units. The final assembly process transforms individual glass components into complete architectural systems designed to withstand the extreme forces that skyscrapers experience from wind, earthquakes, and thermal expansion, while maintaining perfect seals against weather for decades. Structural glazing systems must support panel weights exceeding 800 pounds, while accommodating building movements that can shift panels several inches during high wind events or seismic activity. Frame fabrication uses high-strength aluminum alloys specifically engineered for architectural applications, with thermal breaks that prevent heat transfer between interior and exterior frame components. Advanced extrusion processes create frame profiles with complex internal chambers that provide structural strength while accommodating drainage, thermal expansion, and installation tolerances that ensure proper fit during building construction. Glazing compound application requires materials that remain flexible through temperature extremes while maintaining weatherproof seals against driving rain and extreme weather conditions. Structural silicone sealants cure to form permanent bonds between glass and frame components, creating connections stronger than mechanical fasteners while allowing controlled movement that prevents stress concentration during building flexure. Quality testing of completed architectural glass systems involves structural testing that simulates the extreme conditions panels will experience during their operational lifetime. Wind load testing subjects panels to pressure differentials exceeding 150 pounds per square foot while monitoring for deflection, stress concentration, and seal integrity. These tests ensure that panels can withstand hurricane-force winds without failure or water infiltration. Thermal cycling tests expose completed panels to temperature extremes that simulate decades of seasonal weather changes in accelerated timeframes. Test chambers cycle panels between -40 degrees Fahrenheit and 180 degrees Fahrenheit hundreds of times while monitoring for seal failure, stress cracking, or performance degradation. These tests verify that panels will maintain performance through the extreme temperature swings they'll experience in actual building applications. Water infiltration. Testing subjects panels to driving rain conditions that exceed the worst natural storms, using spray systems that apply water under pressure while monitoring for any leakage that could damage building interiors. Air infiltration testing measures how well panels prevent unwanted air movement that would reduce building energy efficiency while compromising occupant comfort in extreme weather conditions. Impact resistance testing verifies that safety glass systems can withstand accidental impacts and extreme weather events without creating dangerous situations. Standardized testing uses steel balls and pendulum impacts to simulate hail damage, wind-borne debris, and human contact scenarios. Panels must either resist damage completely or fail in controlled ways that don't create falling glass hazards. Acoustic performance testing measures how effectively glass systems reduce noise transmission from exterior environments, particularly important for urban buildings where traffic and construction noise could affect occupant comfort and productivity. Specialized test chambers measure sound transmission through completed panels across frequency ranges that include everything from low-frequency traffic noise to high-frequency construction sounds. Optical quality assessment ensures that architectural glass maintains visual clarity and color consistency across entire building facades, where even small variations would be immediately visible to building occupants and observers. Advanced photometric testing measures light transmission, reflection, and color properties using calibrated instruments that detect variations far smaller than human vision can perceive. The manufacturing facility operates advanced inventory management systems that track every panel through production while coordinating delivery schedules with construction timelines that often require glass installation in specific sequences. Computerized tracking systems monitor panel location, processing status, and quality test results, ensuring complete traceability for building components that must maintain performance for decades. Packaging systems protect massive glass panels during transportation using custom-designed crates and cushioning materials that prevent damage while minimizing shipping volume and weight. Each panel gets individually wrapped and secured using materials specifically chosen for compatibility with glass surfaces and sealant systems. Shock monitoring devices track handling conditions throughout shipping, ensuring quality maintenance from factory to construction site. Installation coordination involves detailed planning that accounts for building construction schedules, weather conditions, and crane availability, because architectural glass installation often requires specialized equipment and precise timing. Technical support teams work directly with construction crews to ensure proper handling, installation techniques, and quality verification during the construction process. Environmental impact analysis reveals that high-performance architectural glass significantly reduces building energy consumption through improved thermal performance and daylighting that reduces artificial lighting requirements. Advanced glass systems can reduce heating and cooling costs by over 40% compared to standard glazing, while improving occupant comfort and productivity through better natural lighting and temperature control. The facility's sustainability programs include comprehensive recycling of manufacturing waste, energy recovery from high-temperature processes, and water treatment systems that achieve near-zero discharge. Glass cullet from production waste gets immediately recycled back into the furnace system, while energy recovery systems capture waste heat for other manufacturing processes, achieving overall energy efficiency levels that exceed most industrial operations. Innovation continues, advancing architectural glass technology through research into smart glass systems that can change opacity on demand, photovoltaic glass that generates electricity while providing weather protection, and advanced coatings that can actively regulate building temperature. Future architectural glass may eliminate the need for traditional heating and cooling systems while generating more energy than buildings consume. This remarkable facility produces over 2 million square feet of architectural glass annually, enough to glaze 50-story buildings while supporting construction projects that shape skylines around the world. The precision manufacturing and advanced technology required to create architectural glass systems demonstrates how materials, science, and engineering excellence combine to enable the stunning buildings that define modern architecture. Research and development efforts continuously push the boundaries of what's possible with architectural glass, exploring new coating technologies, advanced manufacturing techniques, and innovative glass compositions that promise even better performance and sustainability. Future skyscrapers may feature glass walls that actively manage building energy while providing unprecedented clarity and beauty. And there you have it, the absolutely incredible journey from ordinary sand to the massive glass panels that create the stunning skylines of modern cities. The precision, innovation, and engineering excellence required to manufacture architectural glass showcases how advanced materials technology enables the breathtaking buildings that shape our urban environments. What other construction technologies would you like us to explore? Drop a comment below and let us know what you think. And don't forget to like, share, and subscribe to keep exploring more fascinating industrial journeys with us.